Hi folks, this is the old fossil here. Today's video is about a 1-bit A to D converter. It uses what's called delta sigma modulation. Oh, by the way, I found out it plays music pretty good too. Delta is the Greek letter used for differences, sigma is the Greek letter used for sum. Basically it works by taking the difference between the input signal and a reconstructed copy of the output. I did most of my circuit design back in the late 60s and early 70s, and believe it or not folks, that was before the world was really digital. The only computers were IBM mainframes that took half the building. The other half was full of air conditioning so they didn't melt. And there was a great rising demand for analog-to-digital converters to feed this new digital monster that was appearing on the horizon. Okay, here's what it looks like. This is the AC times 10 channel. Not much to it. You can see it gets a little busy up here around the comparator. I probably ought to build a PC board. We'll get around to that. My breadboards are concept development. They're not really prototypes or production development or production models, for goodness sake. They're concept developments. It's kind of Rube Goldberg, but the only important thing is they work. This is the flip-flop, dual flip-flop package, and this is the ring oscillator. This is a schematic for the AC times 10 channel. Most of the audio sources that I have around are earphone jacks from MP3 players or computers, and they're fairly low level, like 100 millivolts. So I decided we needed about gain of 10, so that from the reconstructed output signal, here's the little RC filter, there's a 10-to-1 voltage divider here, so that basically what we're comparing is 1/10 of the output to the input signal. That means that basically the output signal will be 10 times bigger than it used to be. It has to be AC coupled because 10 times a DC offset would throw it off scale. There's two fairly low value resistors here making an artificial ground node about halfway between the supply. Same arrangement with the flip-flop and the oscillator. I made the oscillator out of TTL this time, and it's significantly faster. It goes almost 10 megahertz. The time constant of the reconstruction circuit is about 5 microseconds. And this is what it looks like. The TTL oscillator looks like it's about, well, the counter says 8.6 megahertz. The horizontal scale is 0.05 microseconds. So you can see that the output is only ones and zeros, and what's changing is the relative time that it stays ones or zeros. And so it's a 1-bit A to D converter. Right now it's playing music. That's what it looks like. It's my music library. Okay, that's a good one to start with. That's always good test. Straight from vinyl discs. One-bit A to D converter. The little resistor capacitor reconstruction network is really all it takes to convert the delta sigma modulation back into audio. This is not very complicated for the recovery circuit. However, the pulse train's coming at 4 to 10 megahertz, so if you're going to run it any length of distance, you're going to probably need something like Cat5 or coax. I don't think regular old audio twisted pair is going to work. But In specialized applications where you need a lot of reconstruction circuits, that's really cheap. The other thing is that from the little modulator itself, you can take the up and down outputs from the flip-flop into a binary up-down counter. And I've forgotten, I think the part number is like 74193. I've forgotten if that's the binary counter or the BCD up-down counter. And oh, by the way, at this point here, you'll have 8-bit PCM, which you can send to an R2R ladder and recover analog. This is real audio analog to a buffer amplifier. So there's other things you can do. The 1-bit A to D converter is actually fairly flexible and can do other things. There's one more thing. I'm not trying to sell you this to replace your MP3 videos and your streaming stuff. Not at all. 50 years of progress has made good audio, excellent audio. Modern players, like the little Android machine that's recording this right now, and the codecs in your telephones, are excellent. But they're complicated. This technique is from the old simple days, and it doesn't need any software. Thanks for watching. See you next time.